Hi folks, so we're looking at introducing another set of double angle identities that should fall out pretty quickly from the sum and difference ones that we've already learned. These identities may actually be more important to know than the sum and difference ones for the fact that they tend to show up a little more often when you're doing calculus. So let's pay close attention. What would be great is if we could just take this 2 and pull it out to the front and say that the sine of 2 theta equals 2 times the sine of theta. I'm hoping, though, that you're already fairly skeptical of this because so far nothing has seemed that easy. And if we think graphically right, we can know already very quickly that these two sides of the equation are not going to be the same thing, right? If we were to graph the right-hand side, we know we'd have an amplitude of 2. But if we graph the left-hand side, our amplitude would just be 1, and our period would be much different, right? I guess it'd be pi for this one, 2 pi over 2, and for this one would just be 2 pi. So right off the bat, we can say no. And then, of course, a quick counterexample will also work. Perhaps the easiest counterexample to check on this would be just use 30 degrees in place of theta, right? And we know the sine of 60 degrees, 2 times 30, is not going to be the same thing as 2 times the sine of 30. And we can see the results there. So, of course, the question becomes, what does the sine of 2 theta equal? And we can approach this by looking at some of our sum formulas. Without looking, maybe pause the video and see if you can write down the sum formula for sine. Perhaps you've learned the cheer and can use that to do it. Is this what you wrote down? Yes, so maybe you were thinking sine, cosine, cosine, sine, part of the cheer, right? That's the first part of the cheer that applies, and it applies to the sine identity. And we do not change the plus, that stays. All right, so what we can do here with this identity now, of course, is we can we need to get something that adds up to 2 theta here. So I know I was using alpha and beta, and maybe you didn't use that, but now I can substitute, right? Instead, we're going to go with the sine of, well, to get the sine of 2 theta, we need to think of that as the sine of theta plus theta, right? So, why don't you pause the video and see what you get when you apply this sum identity to the sine of theta plus theta. Just let one of the thetas be your alpha, the other be your beta, and see what you get. Is this what you got? So if you apply the identity appropriately, you should have sine theta cosine theta plus cosine theta times sine theta. And then hopefully you recognize that those two terms are actually like terms, right? We can just flip the cosine theta and the sine theta, and we can see they're the same term. So we actually end up with 2 of them, right? It's like having xy plus yx will give you 2xy. All right, and that is our identity for our double angle identity for sine. So maybe put a box around that. That would certainly be something to have in your notes. Okay, so let's see if we can verify this identity here with our example we were using before. So we're going to let theta be 30 degrees. Let's see if the sine of 60 degrees, right? That's what we have on the left-hand side. I want to see if that is equal to 2 times the sine of 30. Now that would be 1/2 times, and then the cosine of 30, of course, is root 3 over 2. And the 2 and the 1/2 will cancel and leave us with, that's supposed to be times right there. That should leave us with root 3 over 2, and I believe that is correct, right? That is the sine of 60 degrees. So looks like this identity is working. So we should be able to apply the same method to determining the cosine of 2 theta. So why don't you pause the video, see if you can write from memory what the sum formula is for cosine. Is this what you wrote? So we're using the second part of the cheer to write this one, right? The cosine, cosine, sine, sine, sine. And we say sine 3 times, remember, because the first one is reminding us to change the SIGN from what we see over here. So if that's a plus on the cosine one, this will be a minus. So that you're right with sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. All right, so why don't you apply this to the following expression here to see if you can come up with an identity for cosine of 2 theta. As with the one for sine, it'll be in terms of sine and or cosine. Check and see if this is what you got. So let's see, as with the sine of 2 theta, we can write cosine of theta plus theta and just let the theta be both our alpha and our beta. And this time, though, we end up with cosine squared theta minus sine squared theta. Kind of interesting. It almost looks like the Pythagorean identity, but we've got the minus. And you do need to make sure that the cosine comes first. All right. So yes, this is our identity for cosine of 2 theta. Now the interesting part is, from that last question you guys answered, there were actually 3 answers in there that were correct, this being one of them. But because we have these squares here, we can actually write the double angle identity for cosine in 2 other ways as well. So if we would like to, we could actually kind of rewrite this so that there's no cosine in this identity. So see if you can apply the Pythagorean and get this cosine of 2 theta equals something that just has sine in it. Sine theta, that is. All right. Is this what you got? Yes, so if we change cosine squared to 1 minus sine squared, kind of good reminder to put parentheses in here, but it doesn't matter as much for this case. But we will end up with 1 minus 2 sine squared theta, right? Because we've got a negative sine squared theta minus another sine squared theta. So here is a form of double angle identity for cosine that has only sine theta in it. All right, and now see if you can come up with the double angle identity for cosine that just has cosine in it. All right, so you want to think about replacing sine squared of theta. Is this what you got? This time it is kind of important when you replace the sine squared of theta with 1 minus cosine squared of theta that you have parentheses around it, because that negative will distribute and give you a plus cosine squared of theta. So yes, you should end up with 2 cosine squared theta minus 1. And that is the third variation on the cosine of 2 theta. Now that we have the double angle identities for sine and cosine, it shouldn't be too hard to get a double angle identity for tangent. So why don't you pause the video and see if you can come up with a double angle identity for tangent using what you know about tangent. And it's okay if it has sine of theta and or cosine of theta in it, but make sure it doesn't have, you shouldn't stop at having sine of 2 theta or cosine of 2 theta. We want to get down to just sine or cosine of theta, or possibly even tangent of theta, but see what you come up with. All right, is this what you got? Yes, so of course tangent of 2 theta is sine of 2 theta over cosine of 2 theta, and then we can apply our double angle identities to sine and cosine. Now with sine, we had no choice. You have to use 2 sine theta times cosine theta. But with cosine, you could have used one of the 3 that we have. I just went ahead and used the first one. That tends to be the one that I remember best. I just think, hey, it's Pythagorean, except for the minus, and it's got a cosine in front of it. It's got the cosine first. Now the thing is about this identity is most of the time textbooks don't write the identity this way. I mean, this is not wrong, but they usually like to have the tangent of 2 theta just in terms of tangent of theta. Okay, so we're going to employ a little scheme to do that. Here I'm going to moving my thing over, and so what we want to get just tangent everywhere, what we need to do is divide everything. I think we did this maybe once before with the sum identity. Divide everything by, cosine, okay? And more specifically, we're going to divide everything by cosine squared on both the top and the bottom. We have to use cosine squared, right? Because we need to change this to tangent. We've got sine, a sine squared, but it also works out on top, right? Because all right, so we're going to divide by cosine squared, which is multiplied by 1 over cosine squared. And when we distribute that, it works out fairly nicely, right? Because, oops, I meant to change back. Because we're going to have this cosine canceling out one of these cosines, and then we'll have a sine theta over cosine theta. Then, of course, over here, we'll have this canceling out, the cosine squares canceling when we distribute, and then be left with sine squared over cosine squared. So it works out really nicely to give us. I think it's important to note the difference between the numerator and the denominator here, right? Since there's a times here, we're not distributing really this 1 over cosine squared. We're just multiplying it, and so we can put one of those cosines underneath the sine and one of them underneath the cosine. But on the bottom, right, we have the minus, so we have to distribute across that, and so that's why we have cosine squared on the bottom everywhere here. And this gives us 2 tangent of theta all over 1 minus tangent squared of theta. All right, I am realizing some of you might have done this a little differently, so I wanted to show you very quickly, just on the next screen, the way you could have applied the sum identity for tangent. Perhaps that's how some of you did this. It's probably easiest to get the double angle identity for tangent in terms of just tangent by simply using the sum identity for tangent here, right? That's tangent of alpha plus tangent of beta. It's the distribution of tangent in the numerator, and then all over 1 minus tangent of alpha times tangent of beta. And so, of course, if our alpha and beta are both theta, we'll have tangent theta plus tangent theta over 1 minus tangent theta times tangent theta. And on top, we'll end up with 2 tangent theta all over 1 minus tangent squared of theta. Okay, so let's summarize on the next page. So we have 3 new identities to learn. Of course, one having 3 parts to it. I would say most importantly, learn the sine and the cosine, right? As you saw, if you know those 2, you can get an identity for tangent using those 2. And I'll just point out with the sine one, of course, there's only one here. Remember we had originally asked, does sine of 2 theta equal 2 sine theta? Well, it almost does, right? We just have to remember we also have that times cosine theta, that extra little piece there. So it almost is that you can just pull the 2 out. And then the cosine one, as I was saying before, I usually just try to remember the top one, cosine squared minus sine squared, because I am pretty confident that if I need to get the one that just has sine in it, I know how to replace cosine squared with 1 minus sine squared, and vice versa. If I need to get the one that just has cosine in it, I can do that pretty easily from this top one. It's a little harder if you remember, say, the cosine squared one, and then try to get the one that just has sine squared in it, or the one that has both in it from that one. So, as I said, I go with the top one first. All right, so have all these in your notes, and you will be applying them on some homework to come very soon.